Hello. Today we're going to talk about Chapter 6, which is scatter plots, association, and correlation. Okay, so a big part of statistics. Well, everything's a big part of stat, it seems. All right, anyway. So, sometimes we ask ourselves, these types of questions. Are grades actually higher now than they used to be, right? Things like that. Do people tend to reach puberty at a younger age than in previous generations? Do applying magnets to parts of the body? Blah, blah, blah. All right, we can graph these in a way that make it easier for us to understand. So like, for instance, here's a time plot of the mean error of the predictions of hurricanes. So here you have your years, and then here's how far off they were off in nautical miles. So that's how far off they were with their predictions. Okay, so here, important thing to notice is that there is no origin, right? Because we have time and prediction, and usually our values, it wouldn't make sense to have 0, right? Year 0, that doesn't really make sense. All right. So here we're looking at two quantitative variables, right? Something that we can easily compare, and we can track them on this scatter plot. Okay, so we want to be able to tell if there's an association between the two. Okay, so an association is more like a relationship. Okay. All right, so when you look at a scatter plot, okay, you're going to describe it. So there's 4 things that you're looking for. You're looking at the direction, the form, strength, and anything unusual. So the first thing is, when you look for direction, you're looking for a sign. Well, here, notice this is like having a positive linear slope. So that's why this one, it would be positive. Ooh, my handwriting got atrocious. Positive. There we go. Okay. While this one over here, you can clearly see that that has a negative direction. So that's what it means by look for direction. You want to be able to tell the sign whether it has a positive relationship or a negative relationship. Then you look for the form. You want to look for, is it straight, curved, or something exotic. All right, so here almost looks like a slight curve, could be linear. This one, it's doing something a little bit weird, right? We don't really like this. Okay, so this is, we can't really have a way to describe this with statistics. Okay. Then so form is just kind of like the shape. So what's it looking for? We would ideally look for a linear shape. That's what we're looking for. Ideal is linear. And now for the strength is basically how close-knit everything is, right? It would be great if everything was on a perfect line, but that's unrealistic. Okay, so here this has a very strong relationship. All right, the strength is very strong because they're very tight knit. Here, it's very scattered. Okay, so it looks like there's 0 strength. Okay, or not 0. We don't want to say extremes. We want to say exact like that. Okay, sorry. All right, so for the unusual features, you want to look for things that you don't, how do I put this? Your outliers, things that don't make sense. Okay, it helps to look for things that it points out weird stuff. So like, for instance, for this one, maybe you need to reevaluate your data and look at these points together and these points, and maybe there's a relationship there, so you can separate it. Okay, so that's what it means by looking for clusters or subgroups or something to like separate your data. That's what scatter plots do. They help us see the relationship between our variables. Okay, all right, next one. So here we've got 4 examples. Okay, so this is how I would explain each one. Okay, so this one is a positive linear straight, okay, and moderate in strength. Okay, it's not super strong because I still have some that are a little bit further out. Like if I were to draw a line right here, I still have some that are pretty far away. Okay, whereas opposed to here, they're all pretty close knit together and kind of form that curved relationship where this is negative because it's going down. Okay, here it appears negative, right? Slightly negative. Okay, not like a small slope, but we wouldn't really say that, just say negative is fine. Then linear, but it's very weak. Okay, it's very scattered. So weak means it's very scattered. Okay, and it does have a high outlier. So if you ever notice one that's standing out, you want to mention it. Okay, now for this one, there's nothing going on. Okay, there is, appears to be no association. Okay, so that's how I would describe these four. Okay. Okay, so in these examples, the two variables play very different roles. Well, not very different, but they're different. We want to call them not just x and y's, okay, but something called the response variable and the explanatory variable. Just placing a variable on the x-axis doesn't necessarily mean that it explains or predicts anything. So usually when we do a scatter plot, we just assign one as x and one as y, and then we look for a relationship. You have to think about what you're looking at, your data, what you're trying to figure out. Your question will tell you what is x and what is y. Okay? So for example, we can do these. So for this first one, I would say that the explanatory variable would be the total number of runs. Okay, so what the score is. So the team score. And then the response would be selling more tickets. Okay, well, I guess number of ticket sales. Okay, and this would be the team score of runs. Okay, so you want to be more explain more there. So then here, do older houses sell for less than newer ones of comparable size and quality? So the explanatory here would be the age of the home, and the response would be the sale price. Okay, so does the age of the house affect the sale price? So for the next one, sometimes just thinking about it as a timeline can help. You know, you take your SATs first, so I would make the SAT score my explanatory variable, my x, and my response variable, I would make it my GPA in college. Okay, because that's we want to see if that's an effect from our SAT score. Okay, well, not really an effect. We don't want to say it's cause and effect. We just want to see if there's a relationship. Okay. All right, now again, that's what they mean by this. You know, it doesn't necessarily mean that it's going to have that relationship, but that's how you kind of read your data and kind of assign it by what you're thinking. So for this one, we want to estimate a person's body fat. So since we want to be able to predict that, maybe we should make E, our explanatory variable, our waist, our wrist size. And then the response variable would be body fat percentage. Okay. Now let's dig into how they're related. So here we have some data that was collected that included students' height and weight. Okay. Now we want to see if there's a relationship between the two. Well, the first thing we can do is, well, we can think about, okay, does it matter if I measure it in pounds and inches, or if I change that? Okay, do you think my relationship, my scatter plot, would be different? Okay, hopefully you said no. Okay, it doesn't matter if I switched to kilograms and centimeters, I still am going to have the same kind of relationship, the same kind of scatter plot. So before we were able to normalize our data, here we can do the same thing. If we're trying to find the relationship between it, we can standardize the data. Okay, so what we do is we're basically taking each data set value, right? There's an x and a y, so we take each x and y, subtract the corresponding mean, corresponding average, and then divide by the standard deviation. So that's going to find, okay, we're standardizing it, okay? Okay, so our z-scores, right? We have our standardizing, we get our z-scores. So now I'm going to color code these dots and talk about what the z-scores represent, okay? So here we have a z-score where the green, that's a positive relationship, okay? Those z-scores represent positive because both z of x and y, the z-score of x and y, are positive. Both down here, when they're both negative, we'll think of it like a negative times a negative makes it a positive, okay? The kind of purplish, whatever color that is going to be your negative relationship. And the blue dots, which I'm not really sure why those ended up a little bit blue, but these blue dots that are on your axes, those would be like a zero relationship, so there's none. Okay, that's what those different z-scores represent. Okay, so again, those data sets represent the direction and strength of the points. Okay, so let's see what we can do to, yes, we can talk about one data set individually, but if we want to see how it's related, we want to look at everything. So we look for a correlation coefficient, which is called R. So R in statistics will always mean the correlation coefficient. Always, 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 nothing else. Okay, so it's when we add up all of the product of those z-scores, and then we divide by, well, in what we do in statistics, n minus 1, right? So you're basically taking the average. Okay, yes, just roll with me on n minus 1. It's just what we do. Okay, we'll get to it later. Okay, so let's do an example that might help with this. Okay, so because we'll get the R value off of our calculator. So before we know we can use the correlation coefficient, okay, we have to make sure these things are true. If these things aren't true, then we cannot use the correlation coefficient. It's one of those things, it's super easy to do and super easy to get, and then people just use it without even thinking, okay? So first of all, you have to make sure it's quantitative variables. Okay, you can't do categorical, it's not going to make sense. You can't put categories along an axis. You can't put one before the other, okay? So it has to be quantitative data. The second one is the straight enough condition. That's when you literally just look at the scatter plot and go, yeah, that kind of looks like a line. That's a judgment call, okay? It's not a hard one to make. It either looks like a line or it doesn't look like a line, but you cannot do this correlation coefficient if your graph is not linear, okay? We're not doing any other kind of relationship. It has to be linear for the correlation coefficient, okay? The no outliers condition is huge, okay? So you have to look at the scatter plot. If there's an outlier, it can change everything. It can make a weak association be strong. It can make a strong one look weak. And it can even change the sign from a positive relationship to a negative relationship. So your R can be drastically affected by an outlier. So be very cautious. Ooh, I don't know why my computer edited that, but whatever. Okay, so be cautious in interpreting or accepting others' interpretations of the correlation coefficient. Because if they don't give you the scatter plot, if they don't show you what they were doing, then that correlation coefficient could be useless, okay? It's a judgment call. If you use R, give people the scatter plot, okay? Have to make a judgment call on your own because people manipulate this stuff, right? Okay, so let's make sure we understand what the correlation coefficient is. I like this just checking box, okay? So I'm telling you, right? I'm telling you that the correlation between the scores on exam 1 and exam 2 was 0.75. So the correlation was this value, 0.75. So before answering any questions about the correlation, what do you need to see? Well, I hope you answered. You need to see the scatter plot, okay? Because if you don't see the scatter plot, you can't do the straight enough condition and the outlier condition. You need to check that on your own, okay? So if someone gives you R, ask for the scatter plot. All right, so now if I add 10 points to each exam 1 score, will that change the correlation? So if I change all my data sets, or all my data plus 10, I hope you answered. That's not going to change anything, right? Adding 10 to all my data set, I mean, it shifts everything up, but how they're related to each other isn't going to change. So then let's see, if she standardized the scores on the exam, will that affect the correlation? Well, getting those z-scores, it better not. Okay, that's how we want to see if they're related. So if the z-scores don't get changed, then that's not good. Okay. Number 4, if someone did poorly on exam 1, are they likely to have done poorly on or well on exam 2? Well, the correlation coefficient is 0.75. So that's telling us direction. So think of that like slope. So this is a positive relationship, so I know it's going to be like a positive line. So if this is exam 1 and this is exam 2, then yeah, if I did bad on exam 1, I probably didn't do so hot on exam 2, right? Because it suggests a positive relationship between the two. Okay. All right, so if someone did poorly on exam 1, can you be sure that they did poorly on exam 2 as well? Well, we can't be entirely too sure, all right, because the general association is positive, but people are different, right? Yes, we have this relationship, but our data set could look like this. Right? And then look at that. I've got an outlier. Well, no, I don't want an outlier. Nope, just kidding. I don't know why I said that. I meant to say that one just looked higher. Okay, so it's higher than what we expected. So maybe they didn't do so well on exam 1, but they did much better on exam 2. Okay. So like individuals vary, right? You can't always predict them. Okay, so let's practice getting the correlation coefficient ourselves. So we're going to use the tuition costs at Arizona State. So we're going to stat, edit, and your textbook shows you how to rename them. Personally, I find that, I don't know, I just don't see it's worth it. I just know list 1 is list 2, or what they are, but make sure you write them down. So, for instance, I'm going to put the years, 1990 to 2000, for list 1. And then I'm going to do the tuition for list 2. Okay, and these are respective. And what I'm going to do is I'm probably going to do my 1990 a little different. So let's see, I'm going to do what your textbook does, and we're going to do, instead of doing 1990 and dealing with big numbers, I'm going to start with 0 for 1990, and then go up all the way until 1999. Okay, so that's going to get me, oh, I'm sorry, we're going to go to 2000, so I need to go to 10. Okay, 1990 to 2000, so that's 11 data sets. That's why we started with 0. And then type in these. Okay, so there, you want to make sure you get all your data and have all that inputted. Okay, so, oh, I forgot to do this. I always forget to do this, but thankfully your textbook does it. Hold on, I'm finding it. We got to make sure our calculator is set up to find the correlation coefficient, because it may not be. So what we do is we have to hit second catalog. So it's second and then the 0, there's your catalog. And then we're going to go all the way down to diagnostic. Okay, so we're going to go all the way down to D. There's got to be an easier way. I wonder if I just type in the letter. Will that get me there? Where's the letter? Oh, it's in the greens. Ugh, can't see. Oh, yeah, that worked. Okay, so then I need to go diagnostic. Oh, this is all your stuff that your calculator can do. Okay, so we want to turn the diagnostic on, and now our calculator will always find the correlation coefficient unless we, have to replace the batteries or reset it. Okay, so you've got to make sure the diagnostic is on to get your correlation coefficient. So remember, okay? All right, so now we graphed it, or I'm sorry, we have it. I would graph it. You got to make sure your scatter plot looks good, because if it doesn't, then we're just wasting our time. So list 1 is my years, list 2 is my tuition. So zoom stat. And here we go. That looks pretty linear to me. So I think it's safe to do a correlation coefficient. And oh, I have one of my graphs on. Sorry about that line there. All right. Okay. Sorry, this was in words of what I just did to make sure your diagnostics was on. Okay, so this has to be on to do your correlation. So we go to our calculator, go to the main menu. We're going to do stat, go to calc, scroll over. We're going to go to number 8, which is ln reg. It's not number 4, don't be confused. Go to a plus bx. I don't know, I always forget the reason why, but you always want to do this one. Okay, so number 8. My X list is list 1, my Y list is list 2. We're going to calculate. And now it gives us everything. Okay, so it gives us even the line that goes through it, and it gives us R. R is what's important here. It's a 0.993 relationship here. So that's a very strong relationship between the years and the tuition. So it's got a steady increase, probably due to inflation. Okay, but can't really say unless I actually see the data, right? So that was a lot of stuff. Okay, so if you liked all those numbers and all that stuff, you're going to really enjoy the next chapter. Chapter 7 is a big one. It's going to have its own test. But anyway, for now, just care about R. Carry about. That's late. What do you expect? All right. So some fun facts. All right. The sign gives you the direction, right? So a positive R. Oh, gotta get my pen working. A positive R is going to correlate to a positive line. A negative R is going to correlate to a negative line. Crazy. Okay, it's not slope. It's not the actual slope, but it you can kind of think of it like it, right, and help you in that sense. The correlation is always between -1 and 1. Okay, It can actually be -1 and 1, but that's super rare, okay? Because that means a perfect relationship. So a 1-to-1 relationship means it's exactly lines up. It's a straight line. That's very unlikely, okay? Because again, we live in the real world and things are flawed. You know, people are flawed. Things happen. Things go outside average or normal, right? Okay, so keep in mind, it can go to it, but very unlikely. Now, the correlation of x with y is equal to the correlation with y with x. So this is what I mean. It doesn't really matter what you put as the x-axis or the y-axis, because either way, you should get the same r value, the same relationship. Okay? It's not going to change your opinion of the graph, of the relationship between the two. Okay? Correlation is when we are standardizing, thus it has no units. It's just like z-scores, all right? We are normalizing it, so it has no value. All right, and since it depends on the z-scores, they are unaffected by changes in center or scale, okay? Unaffected. So that was that whole adding 10 to our test grades, whatever that problem was, okay? So they're unaffected. Okay, and it measures the strength of the linear association. So when I say the strength, I'm talking about this stuff. How strong is it? Weak, moderate, strong. Use those words, but they have no definition, okay? Meaning that there is no, this makes it weak, this makes it moderate, this makes it strong, okay? Moderate is somewhere around 0.5. Strong, I would say, is probably more than 0.75, right? Weak would barely be around less than 0.25. That's rough guesses, guys, but it really depends on your data, okay? And how strong you want that or need that relationship to be, okay? It always depends on the context, okay? Also, super sensitive to outliers. Made that pretty clear before. Gonna keep saying it. Sensitive to outliers. Gotta get rid of them. Okay, so correlation does not equal causation. We say this over and over again, and even before you took statistics, you heard this over and over again, okay? What that means is just because there's a relationship, that does not mean they actually cause each other. So look at just these numbers, okay? You have this one steady increase, this one steady increase, and we have a strong correlation of 0.97. Okay, so wow, it seems like there's a relationship. And so in our brains, we're humans. We want reasons. We need to logic it out. So we want to say why or how they're related. So we look at this. Get ready for this. Human population. Okay, is the human population affected by the number of storks? Well, storks do deliver babies. So maybe that's true. All right. So what this was is this was a study done in the 1930s, or not in the whatever. The data is from the 1930s of Germany that plotted the town's population along with the number of storks. So in our brain, we want to go, okay, well, clearly more storks. That means more babies are being delivered. I mean, what else could there be, right? You have to think about it logically. Think about your data, right? There actually is a relationship, but it has to do with the house chimneys, okay? More people means more houses, more nesting sites, more storks. So the cause was actually the opposite direction of what we graphed, okay? So you can't tell from the scatter plot or from the correlation coefficient if there's actual cause between the two. You need more info. You need context. Okay? I can't exaggerate that enough. Okay, so here we have, do firefighters increase the cost of damage? Okay, so here we get More firefighters. Okay, we get a lot more. Whew, 40 firefighters. Look at how much more I've got to pay in damages. Well, geez, maybe I shouldn't have those firefighters come over and help me out because clearly, that's just too much damage. We're smarter than that, right? We know that's silly. So when there's an underlying variable, right, because obviously these aren't cause, there's a blaze, right? The fire, how big the fire is. Okay? If the fire's huge, well then yeah, I better hope there's going to be more firefighters coming out there. Please don't send just one Joe Schmo to help me out. Okay? All right. So that hidden variable, okay, is called a lurking variable. Yes, because it lurks there, right? It's just kind of waiting to be caught, I think. Okay, but look out for them. All right, correlation tables. So if you've got lots of data sets, so lots of things you want to compare to. So you've got assets, sales, market value, profits, cash flow, employees. You want to see if any of that stuff is related. They like to make or people like to make a table. Okay, so here, I would hope that the diagonal would be 1 because assets compared to assets better be a 1-to-1 relationship. My data better be related to itself. Okay. But then here, it's got all the R values right there, which is great. However, what's wrong with this? This could be very dangerous. I hope you said there's no proof. There's no scatter plot. How do I know that these are linear relationships? How do I know that there's any relationship at all? Okay, so what if there's an outlier? Okay, I don't know. We can't just look at the R value alone. Okay, so some ideas for straightening a curve. All right, so with a camera, you have something called a shutter speed and an f-stop. So your f-stop is how open, think of it like the diameter of the opening for how much light you let in a camera. Okay, so you have, so here for 2.8, you're going to have a very small opening, but for 32, you're going to have a much larger opening. Okay, so what we do here, and the shutter speed is how long that f-stop, that light, how long you let the light go into the camera lens. Okay, I know it's a digital world and we don't do this anymore, but it's kind of fun to do, right? We use those old-timey cameras. All right, so here we have our f-stop and shutter speed. If we were just to graph those values as they are, we get a 0.979, which is a very good R value, very strong relationship. However, this looks more curved. So we want to straighten out that curve. So what we can do is we can put this data into our calculator. Ooh. And then let's see. When we put it in there like this, so list 1 and list 2. Oh, I guess I didn't notice they labeled it different. All right, but if I wanted to square it, I could literally just take the list 2 and square it. So let's just use the data that I already have in here because I'm lazy and it's 8:50 at night and I'm tired. So if I wanted to square, let's say the second list, all right, we go to, let's see, where is it? Okay, I always forget it's the alpha, or second. Okay, so second, list 2, I want to square, so literally hit the square button, then I'm going to store it as list 3, so second, list 3. And there we go. I've squared all the data set. I can scroll up, and then I can hit the right. Ooh, did I not do that? Maybe I wasn't supposed to scroll up. Uh-oh, I glitched it out. Maybe I can hit it again. Okay, yeah, I don't know why I scrolled up then. Okay, we can look at it there, or we can go into our stat, into our list, and there are our values. And if we scroll over them, we get them written out. Okay, so that's how we could have done it for our f-stop, and then now we get more of a linear shape, which is awesome. And we do get a better correlation, okay, value, but I know this was already good, so you're like, why did we have to go through all that? Okay, because the graph, I'm telling you, the graph is the important thing. If your graph doesn't match and it's not a linear shape, it's useless. The R value is useless. Okay, so in chapter 10, we'll discuss more ways to find a good re-expression. Okay, so we're not going to really we're not messing with changing the data set right now. Okay, but what's important to know is that the form of the plot must be straight. Okay, this is more important. Okay, so let's see. I hope I can wrap this up now. So what can go wrong? Don't say correlation when you mean association. We say this all the time, and I really should watch myself too, that correlation is a strong relationship. The association just means it's more vague. Okay, it's where I don't know what the R value is. It kind of looks like there one. It's like, hey, there's kind of an association there. All right, correlation means that you found it out. Okay, it's proven. Okay, big thing, don't do it with categories. It doesn't make sense. You can't put categories on an axis. Makes no sense. You can't put them in order. Don't confuse your correlation with causation. Make sure it's linear. Don't just assume it's linear just because the R value is high. Okay, you can't assume it. And be careful of your outliers. These are the big main things I want you to know. Okay? And let's see. Basically, this is what we've learned. I thought this was a pretty cute cartoon. You know, hopefully this helps, you know. Well, maybe. Anyway, let me know if you need any help with anything.